Yeah, so really these last 4 questions here is what I want you to focus on right now, is just try things. If you don't have an idea, invent the craziest thing you could think of then. Just see what happens, right? If you can't think, well, how else would I select? That, I don't know, just really just do whatever. Same with mutation, same with crossover. All right, here we go. So, okay, problems. Oh, wait, hold on. Is it problems? And then after problems, we have origin. Okay, I guess it's the next topic where we get into more about what I was saying a moment ago. But let's talk a little bit about problems. So, the maximization of integer values of an unsigned binary number was a toy problem. It's trivial. In practice, you're not using evolutionary computation for this, right? That's silly. Evolutionary computation, it's usually used for hard problems. Problems where we really have no other reasonable approach. And that's the strategy, right? If you have a heuristic for TSP, traveling salesperson problem, use it if it's good. If you don't, use a GA, right? If a heuristic exists, but it's too hard to implement, screw it, use the GA, right? Like these are the trade-offs. The GA will work well, the genetic algorithm will work well, but it won't work better than something designed for that. But for most problems out there, we don't already have existing, for most hard problems out there, we don't have existing good heuristics for them. So, yeah. So, a system. We can break systems down into some input. Now, I'm using the word model here. This is if we're modeling a system. But a system in and of itself has inputs and outputs. And if I'm modeling a system, I would call that system, like I would have a model of it. But typically, we have input into the system and then output. That's how it is. This isn't magical. It could have more than one input, it could have more than one output, that's possible. But this is your systematic thinking. That's a system, all right? It's a simple black box representation. It receives some number of input, performs some operations on the input, and produces some output. And thinking of a system in this way really helps us distinguish 3 important components. For concrete examples, you can think of calculating a grocery bill. We know the prices. The system, the model is just sum up the prices and add the sales tax, and the output is what's the final bill. Okay? Designing an aircraft wing. All right? The input is going to be like the shape of the wing, right? Then if we want to we're going to perform some complex calculations on it, equations with fluid dynamics and whatnot on that wing shape, and the output is going to be estimates of drag and lift. If it's photosynthesis, right? Well, that system receives light, carbon dioxide, and water, and the system itself is there's a bunch of reactions, and what we have, the Kelvin cycle, and the output is oxygen and sugar. Yeah?
Is the input the same at hyperparameters?
No. We're not, take a step away from evolutionary computation now. We're not talking about evolutionary computation, we're talking about something, right? A computer, your input, it does crap, produces output. I eat food, I drink water, my metabolism, every system inside of me, and my output is just me moving around and whatnot and doing everything I do. Everything is like input, the system itself, and the output. Calculating the time it takes to drive to work. Input is the route taken. The model is, well, our fucking universe. And the output is how long did it take, right? Everything. And as computer scientists, we often like to think of models as some function. It is, but we are very explicit about the word function. Take some real world thing. If we want to get all Latin, we say, oh, in vivo, right? Like in living, in life, right? And try to model it in a computer, in silico. That's fancy in the computer. We've Latinized a phrase to make it sound fancy. And with the known model, the output is very easy to compute for any valid input. If I know the model, I give that model the input, I let it do its thing, or that system do its thing, and it produces the output. Now, there are optimization problems. Think of, I want to know the best route to work, right? Well, the optimization really is a matter of like the input, right? The model is going to be like, well, we exist in Antigonish, right? How are we going to get to, like, we know the available routes. The system is our traffic system and how we can, like, the routes and whatnot. And the output is going to be how long it takes us to get to work. But the input will affect what the final output value is. And I want the best route to work. I want to get to work as the fastest I can. So the input, this becomes a problem of, if I want to optimize this becomes a problem of, let's search the various possible inputs for the one that gives me the best output, right? And what I'm saying, this shouldn't be mind-blowing to you. All I'm doing is I'm breaking down ideas and concepts you already know, but I'm really trying to break it down into its parts to talk about it a little bit more formally. Only a little more formally. So yeah, modeling optimization takes place when the model and output objectives are known, but the input is not. I mean, we know what the input could be. We know what admissible input is, routes to work, but we don't know what the best one is. And here we would say the search space, the space of all possible things is all possible inputs for this optimization problem. Path to work that results smallest amount possible, I just explained that. Traveling, sales, well, okay, so just to be clear, this is a formally defined problem defined, I don't know, a long time ago, called the traveling salesman problem. Typically today, people will say traveling salesperson for obvious reasons. But if you go and you look it up on Wikipedia, you're going to find traveling salesman because that's how it was defined 100 and whatever years ago. So just be warned. But here's this taken directly from Wikipedia. TSP can be modeled as an undirected weighted graph such that the cities of the graph are the graph's vertices, paths are the graph's edges, and the path's distance is the edge's weight. It is a minimization problem starting and finishing at the specific vertex after having visited each other vertex exactly once. Blah. Raise your hand if you're not 100% familiar with TSP. Okay, I'll explain. Basically, it is given some graph, find the Hamiltonian cycle. Hamiltonian cycle is basically, you ever play that game as a kid? Put your pencil here and draw this picture without lifting your pencil, right? You know, right? That's the job here. That's your job. We want to come up with a Hamiltonian cycle, but we want to pick the Hamiltonian cycle that visits all cities such that the total distance or the weight of the edges is minimized. So what are my possibilities? If I want to, and we start and end at the same city. It's kind of arbitrary, but let's say we're starting and ending at A. What path should we take? I think I've got some examples below. Okay, I do not. I could go A to B to C, I could go A to B to D to C, back to A, and that's 20, 34, that's 54, 66, no, 66, yeah, 108, yeah, 108. Okay, great, that's one option. But is it the best option? Okay, let's try A to B to C to D to A. So that's 20 plus 30, 50 plus 12, 62 plus 35, so 97. Let's assume I'm right. Well, if you had 108 versus 97, which one's better? 97. I want to go less. Okay, that's another path. What about A to D to C to B to A? 35 plus 12, that's 47, 77, 97. Oh, that's like the same. All right. There's a simple algorithm for traveling salesperson problem. All you have to do is run and calculate the total path lengths of every possible Hamiltonian cycle. And then if you have that, all you have to do is you pick the smallest. Simple, right? It's a very simple algorithm. Try every single possible Hamiltonian cycle and then pick the smallest one. Would you agree that that algorithm, what I just described, is correct and will guarantee you find the best solution? Try them all, pick the best one of all of them. Obviously, that'll get you the best solution. Well, we got a problem. Because the problem arises in, well, how many Hamiltonian cycles are there? Right? How many possible paths are there? Right? Well, if we think about it, let's do a quick think here. I've got 4 nodes. The starting and ending is the same, but let's say it's not. How many options do I have for the first node? How many I know the first and last is usually fixed, but let's pretend it's not. I have to make a decision. Which node do I want to start at? How many options do I have? It's not a trick question, it's just 4. Okay, I pick this one. Now I have to go to the next city. How many options do I have left?
3.
I've got this one, or that one. But let's say I go to this one. How many options would I have left? And then how many options would I have left? Right, so it would be 4 times 3 times 2 times 1. Well, that's factorial, right? Now we can get fancy and be like, well, the first one's fixed, and technically the forward and reverse paths are the same, really, but okay, factorial. So I don't know, let's say I had 100 cities. 100, what's 100 factorial? Oh boy. All right, so yeah, that algorithm of try every single possible Hamiltonian cycle and pick the best one. Okay, yeah, go do that for 9 times 10 to the 157 of them. 100 cities. I mean, 100's not small, but it's not that big, right? All right, yeah, maybe that algorithm, although it'll work, it's not really feasible. But that's traveling salesperson problem. Yeah, okay, think of this in terms of the 3-part system. Given a Hamiltonian cycle, sum the edges of the weights in the circle, and return the total cycle length. But this is just a description of the system, not the description of an optimization problem. To frame this as an optimization problem is, yeah, find the Hamiltonian cycle that produces the smallest possible cycle length. Great. There's a trivial algorithm, the one that I just described. Find the length of all possible Hamiltonian cycles, pick the one with the smallest. Great. Given a set of vertices V, the computational complexity of calculating a cycle length is the cardinality of the set V, right? But that's 1. But the issue was now it's only a matter of applying a linear time algorithm to each cycle, and well, we just saw there's going to be a lot of those, right? So how many cycles are there? The starting here, I said the starting one is fixed. It's factorial, 3 times 2 times 1. So it's 4 minus 1 factorial. That's 6. Here's the possible paths. Half of these cycles are the reverse, though, so you can ignore half of them. But to generalize it, the number of possible paths is going to be the cardinality of V minus 1 factorial divided by 2. And that's a big number. For a reference point, there's about times 10 to the 67 atoms in the Milky Way. There's more possible paths of 100 cities, 100 cities, than there are particles in the Milky Way. So yeah, good luck. I could take a particle in our galaxy and assign it to one permutation, one Hamiltonian cycle for 100 cities, and I'll run out of particles I'll run out of particles real fast. It's crazy, right? N queens, here's a problem. Here's another problem. Place n queens on an n by n chessboard such that no 2 queens can attack each other. Who here is already familiar with n queens? No? All right, that's fine. So one person is somewhat familiar. This is the problem. Basically, I want to place, if it's an 8 by 8 chessboard, I want to place 8 queens on this chessboard such that no queens could actually attack each other. That's the job. Now this is a GIF of it evaluating like recursively for an option. There. That's. It looks like that's probably a valid configuration right there. They don't actually attack each other, right? Unlike TSP, this is a little different though, because it's not really an optimization problem. There's nothing being minimized. Instead, all that's needed is a valid board configuration. It's binary. It's either it's valid or it's not. So that's kind of interesting. With TSP, there's kind of like a gradient. If I had two board configurations, if I had two Hamiltonian cycles, based on the total distance traveled, if I go to the one that has a smaller distance, chances are I'm like making a step in the right direction. There's what we call like a gradient here. There's like, if I had those two options sitting there, and I poured water, and the water wanted to flow to the one that was better, it would flow to the one that's better. There's more of a gradient there, right? There's a pull towards it. You can think of it like a slope. With n-queens, if I gave you two boards, they're not valid, but I asked you which one's better, well, it's just they're both not valid. There's no real gradient there. So it's a little bit of a different of a problem. So how many board configurations are there? Well, it's 64, choose 8, if you remember your discrete math. I have 64, right? And I have to pick 8 cells in them. So how many possible board configurations are there? There's a lot. And here's some problem NASA had. They wanted to make this like a truss, okay? Or they wanted to they wanted to make a truss. It was a truss. Version of the structure was designed by GA to enhance vibration isolation characteristics. With a genetic algorithm, people designed a better truss for NASA. I don't have an image of it, but it looked crazy. It didn't look, no human would have designed it. It didn't look like it would be good at all. But it was like 10,000 times better at like being stable towards vibrations and whatnot. Or how about this one? They wanted to design an antenna. Here's the antenna. Does that look like anything a human would design? I mean, maybe, but why the hell would it look like that? I mean, I think there might be another picture. No, there's not. But that's the antenna. That was designed with the genetic algorithm. And it's better than anything designed by an engineer. Something interesting about evolutionary computation is it can surprise you. We are biased by our preconceived notions of what an antenna should look like and what a truss should look like. A GA isn't. And maybe that's a bad thing because we like to exploit what we know is good, but maybe what we think we know is good isn't good. And by the way, look at the scale of this. It's itty bitty. And it was real good. It's like on satellites and shit. Now modeling. So modeling is a little different when we're talking about the separate parts of a system. Modeling is, well, we want to actually come up with a model of that system. Writing software is modeling. Sometimes it's a simple problem like writing a program to calculate a grocery bill. The input is the things they want to buy and the output is what it costs. The model is just my program of that system. But sometimes it's complex, like writing a classifier for iris classification based on petal and sepal size, right? Write a classifier for that, right? Well, that's not really easy. And who does that? No one does. We use machine learning for that, right? Because it's too hard to do it. When using machine learning and AI for modeling, one can think of this as an optimization problem. It's kind of interesting. We kind of flip a modeling problem into its own optimization problem, where we use like the AI or the machine learning algorithm to optimize the model, which is kind of neat, but whatever, not that important right now. And real-world problems. Find a model that best describes the relationships in the brain based on fMRI data, right? We've got regions of interest, tiny little blips in the brain that seem to have cohesive function. And when you look at a picture of a cat, how do those pieces of the brain work together in relation to one another, right? You use evolutionary computation for something like that. And simulation is the opposite. It's like the third one. Simulation occurs when the input and model is known, but the output is not known. So here's the situation. Here's my input. Here's my model. What's going to happen if I let it go? Okay? We usually do simulation when real-world experiments are really not feasible. Whether it's just too difficult, too expensive, unethical, who knows? But simulation. All I've just described to you are things that you should all be, like in terms of the model or the system, input, system, output. Everything I just described shouldn't be catastrophically new to you. You should already be relatively familiar with these things. I'm just making sure we can break these things down into their bits, input, system, output. And we're aware of like, well, sometimes there's optimization, sometimes there's modeling, and sometimes there's simulation, right? It depends on the goal and how we're using the system. So far, so good? Nothing crazy, right? Now, search problems. Here's an example search space, or sometimes they'll call it a fitness landscape in the context of evolutionary computation, because fitness is our metric of goodness. This example has 2 dimensions plus a z dimension representing fitness. As the location in 2D space changes, the fitness value changes. So for some reason, maybe I'm looking, like I think I already used this example in this class, I want to find the warmest spot in this room, right? So the 2 x and y coordinates, that corresponds to where I am in the room. But maybe the z corresponds to the actual temperature, right? So as I move through this space, I'm searching for the warmest spot in the room. Maybe I go here, it gets a little cooler. There's a low part. I step this way, it gets a little warmer, even warmer, a little cooler, and so on. This is my search space. With the toy problem, maximization of a binary number, you could think of it as you have a space of all possible strings of zeros and ones, right? If you were to draw that kind of as a plot like this, you would get some interesting, like how would that look, right? Think of that for a second, actually. I have a space that holds all possible binary strings of length n, and I want to kind of visualize one axis of that as those that are better in terms of fitness, right? Well, it would depend on what the fitness metric is, of course. How am I measuring goodness, whether I'm using that one's fitness or value fitness? But try to think of how that would look, like the search space would look here.
No, I was just going to say.
What were you going to say? Yeah.
So like I'll say it's a bit string of 3, so that way you can actually pick on a graph. Actually, no, it only has to be what you can pick on a graph. You can expand it to any dimensions, but it basically be like a sheet kind of going up like that, because there's only going to be like one maximum value for each. So it's kind of like, I don't really know how to.
I know what you're saying, right? Yeah. So if you had like 2 dimensions, so it's a 2-dimensional bit string.
Yeah.
And we have like, I'm gonna try. Where we've got like here we've got 0, 0. This is going to try to be like z, okay? Now let's assuming we're using the ones fitness, okay? And then how do I? This is not easy. Yeah, are you following me? The look on your face is making me like, oh, it's not going good. Okay, 0, 0. Let's move 0, 0. And then here we have, it's called a 0, 1. But 0, 1's clearly, you know, higher, right? Right? I don't know. Does that help? Right? And then here we can have 1, 0. Yeah, you with me? And then here we'd have like 1, 1. But of course that's even like, oh God, But you see what I'm saying? Is that what you were envisioning, right? That you could have something like that, and that's even higher, right? That's even better. But it would look different if I had the other fitness, where it was just the integer value. It would be like this, where this is higher, but then that's higher, and then that's even higher. Where here, these actually are kind of sharing the same like plane on the z-axis. It totally makes sense. Just go with me. It's bad, right? Totally. Yeah. If you don't understand it, it's your fault, not mine. It's not my whiteboard skills, no. If the search space is small enough, it may be possible to literally enumerate all possible options. But if it's huge, sometimes it can even be infinite. If you're dealing with real numbers, yeah, it's just not happening, right? When framing problems as a search problem, one can think of a problem solver as some mechanism that traverses the space. If you're using some algorithm to help you find, if you're optimizing, that algorithm is, you can think of it as like literally like some little robot moving through that space to try to find the best point. It's traversing that search space. A GA is traversing the search space of all possible Hamiltonian cycles when working with TSP. And when you think of it like this, it allows us to kind of, we're framing a question a certain way. It allows us to ask questions like, well, what's a good way to traverse this search space? Can the search space be changed? Can I alter it? Can a feature of the search space be exploited? Do I know the search space to be like convex or concave? Meaning I know that if I found a gradient going that way, I should really follow it because there's a chance it keeps going that way. So like you can think of convex or concave, right? If you want to maximize or minimize, think of like a spoon, whether you're holding it this way or this way, Can the search space be constrained or simplified? When you think of a problem like this, it makes it obvious, or it makes it more obvious to ask questions like that. And when you frame questions like this, it helps us reason about how our algorithms could operate a little easier. But I'll stop here for now.